In this example, we're going to look at the cost associated with round-trip flights to major cities between Boston and the city indicated. So, first of all, in part A, it asks us to identify the predictor variable and the response variable. Now, on this one, I've kind of played a little trick on you here, and that is we're very used to having the x value always kind of be on the left and the y value being on the right. That's usually how data is presented to us. But in this case, when we think about the miles traveled and then the cost of the ticket, it definitely seems like miles is the more appropriate predictor variable and cost is the more appropriate response variable, right? Because, you know, it's the distance that ought to be affecting what the cost is, right? So we're going to just note that miles is going to be our x and cost is going to be our y, meaning that our predictor is equal to miles and our response will be cost. So on the next page here, we see what we've seen in the previous example. We have an output from StatsCloud that gives us the important information about the least squares line that we can fit to this data. And then we'll also check the residuals, which you can see in the chart down here, for signs that a linear model is appropriate. But first, I do want to go back through the process of actually producing this output here and this residual plot here just to remind you of how that works. So in StatsCloud, I've already put the data in, and one thing you'll notice is that I went ahead and put the x first and the y second, just like I'm used to, as opposed to the order it was put in our table. So miles is our predictor, cost is our response variable. So remember to come up with the output of our least squares line or our regression line. We're going to hit analyses. We're going to run our first analysis. And then we go down to regression and hit linear regression. And then remember, we want to make sure selecting the correct predictor. So that would be miles, and then the correct outcome or response, which would be cost. So I run my analysis. There's a scatter diagram with a line going through it. And then down here gives me the information about what the equation of the line is, along with some other information. And then also, if we want a residual plot, remember the way we produce that is you scroll way down to the bottom. And when you look at cost residuals, you click add variable. And then if you go back to the data screen, it automatically computes the residuals for you. So with that then, I can go back and look at a chart of my residuals. And the way I do that is I make another scatter plot. I select miles, but then instead of cost, I select the residuals variable. And I build my chart, and there it is. All right, so now going back to our slide, that same information. First of all, let's talk about the formula itself. So to find the slope of my formula, I'm going to go to the x value, and then this number right next to it is my slope. So I'm going to say cost, my predicted cost is 0.080 times x, which is my miles, plus that y-intercept that I see there, 162.596. So there's my equation. Now this other part that says check the residuals for signs that a linear model is appropriate. Remember, the main thing we're looking for is there random scattering in the residual plot, or is there kind of a pattern? Well, if you look this one kind of looks like maybe there's sort of a pattern there. And so what does that mean again? Well, that means that maybe a curve besides a line would better fit this data. Okay, so we'll just make a note here that there's somewhat of a pattern. Pattern indicates a linear model might not be the very best model. But that also doesn't mean that it's completely worthless either. So we might also say, okay, well maybe it's got a little bit of a pattern to it, but I'm going to go ahead and still use my line to make predictions, all right? And we just understand that it's, you know, maybe not perfect. It's not a perfect, well, nothing is a perfect fit for messy data like this, but it's not as good of a fit as maybe we would hope. Just to go back real quick to here, if I go back to our analysis and look at this, so here's where this kind of, the residual plot kind of relates back to this original scatter plot. Would you agree that if I kind of take my mouse and I trace it through here, kind of looks like a curve that kind of does this, might fit the data just a bit better. And so the pattern that we saw in the residuals is manifesting itself in this idea that, okay, a curve here might be a better fit. All right, but setting that aside, let's proceed. So part C asks us, what is the correlation coefficient, R? And so remember, we find that one right here. And so remember that what it tells us is the strength of the relationship and whether it's positive or negative. And values that are kind of in the 0.7s, maybe you'd call those kind of moderate, a moderate relationship. So I would say there is a moderate positive relationship between the miles traveled and the cost of a ticket. Then part D asks us about R squared, right? And so R squared is 0.586. And so 0.586 is telling us, remember, the percentage of variation in the Y value that's explained by our model. So what we would say here is that 58.6% of the variation in cost is explained by the distance traveled. All right, and if you think about this, this makes sense, right? You know, your cost of a plane ticket's going to rely quite a bit on how far you're traveling, but that's not the only thing, right? What city are you going to? You know, there's lots of other factors that go into the price of a plane ticket besides just the distance traveled, but it makes sense that a majority of that variation could be explained by something like distance. Now, part E, we are going to interpret the slope of the model. And so remember, our strategy for that is to write out the slope, but then force it to be a fraction by putting it over 1. And then if we remember that slope is always the change in the Y value, which in our case is cost, over the change in x, which in our case is the distance, then it's really easy to see what this means, right? When the distance changes by 1, which by the way is measured in miles, that means the cost should, because it's positive, increase by $0.08 or 8 cents, right? So for each additional mile traveled, we expect the cost of a ticket to go up by about 8 cents. All right, and then finally part F says, do the data provide strong evidence that a greater travel distance is associated with a greater fare at the 5% level of significance? Okay. So our null hypothesis would be that beta 1 is equal to 0, right? So we're assuming that there's no relationship. So the slope of the line going through the entire population of distance versus cost of a ticket should just be 0. It should be flat line. Where the alternative hypothesis, we could say it's greater, right? Because we want a positive slope, but we'll just keep it general and say not equal to, because that's the output is always assuming not equal to. So I look here and it says that we have a p-value of 0.01. So if we are using a 5% level of significance, that means we reject the null hypothesis, right? In other words, we should not, here we go. It would be very unlikely for a pattern like this that shows a relationship that strong between miles and cost to develop just totally due to randomness. Very unlikely, about a 1% chance of that. So we reject the null hypothesis, so that means there is sufficient evidence at the 5% level of significance to suggest a greater distance traveled is associated with a greater cost of ticket. All right, that's what it means to have a positive slope, right? That as the x value, in this case miles, increases, so does the cost, which is the y value. So for our very last example here, I just want to show an example where the data output looks just a little bit different so that you feel comfortable reading off of this as well. So this one says that the scatter plot and least squares summary below show the relationship between weight measured in kilograms and height measured in centimeters of 507 physically active individuals. First, they want us to write the equation of our line based on this. So it's very similar to what you saw in StatsCloud. So here we have height as the x, we have weight as the y. So this number right next to our height variable, that's our slope. And then this one up here is our y-intercept. So we would say weight is equal to 1.0176 times height minus 105.0113. All right. So like the last one, let's interpret this slope in context. So here's my slope again, 1.0176 over 1, so we put a 1 on bottom. And so we know that this is our change in x, but our x is height. And then up here would have to be our change in weight. So what we have here is that for each centimeter in height gained, we expect a 1.0176 kilogram increase in weight. All right, now it asks us, do the data provide strong evidence that an increase in height is associated with an increase in weight? State the null and alternative hypotheses, the p-value, and state your conclusion. So, we'll say, let's start by assuming the slope is 0, and our alternative will be that, no, the slope, there's a non-zero slope, right? So there is a relationship between height and weight. So here's the p-value. So this one, in the context of this particular data output, is the p-value. What it's saying is it's the probability of being greater than the absolute value of your t, okay? So the reason that makes sense is we know that this is coming from a t distribution, right? So the absolute value of your t, okay, means being further away, t and above, but it also means being at negative t and below. And so that's the reason why this symbol makes sense. But again, we're just going to grab this number here, and what you can see is that the p-value is 0. That means that there is no way, there is no way that this happened just due to randomness. And that makes sense because look, we got 507. You can't really get lucky, right, and have a pattern show up like this if there wasn't an actual relationship in the population when you take a sample size of 507. So that would mean we reject the null hypothesis. So this means there is very strong evidence an increase in height is associated with an increase in weight. Not surprisingly, right? All right, and finally, it says the correlation coefficient R for the height and weight is 0.72. Calculate R squared and interpret it in context. Just real quick here, correlation coefficient is the name of R, right? R squared does have its own name as well. We call this the coefficient of determination. Coefficient of determination. So if you ever see that in homework, in the textbook, anything like that, it's just referring to R squared. So I like this example just because it just reminds us that, R squared is literally squaring this R. So if I want R squared, I'm going to take 0.72 and I'm going to square it. And that gives me 0.5184. So this is telling me that 51.84% of the variation in weight is explained by the model, but the model's only including height, so it's explained by the height. And this makes sense, right? I mean, yes, the taller you are, the more you're going to weigh, but there's also a lot of other factors that factor into how much we weigh. So it makes sense that, yeah, a lot of it depends on height, but certainly there's a lot of variation we see in people's weights that are due to other things as well.